Right. So, hello and welcome everyone. Welcome to this lecture. So, let me share my screen. So, this will be a quick lecture where we have been going a little step by step. We started with something which is very simple like VAs. Then we uh, sort of extended it to HVA, hierarchical VAs. Particularly, we extended it to Markovian HVAs. And slowly we have, you know, now and in HVAs, then we saw that, well, there is, you can derive two uh, o- optimizable objectives. And the later one that we saw is something that we are going to focus on, right? Yeah, and in fact, in last lecture, we saw exactly that. Uh, This was the first objective, and this was the second objective that we derived. And we said that, well, the second objective is of our interest since it involves uh, only a single, it involves expectation over a single random variable. And at the end of the last lecture, we sort of touched upon how are we going to make the transition from HVAs to diffusion models, right? So let's do that transition today and see uh, uh, what it leads to, what it means to, go through that transition. So this is where we'll start diffusion model. So this is ninth lecture. This will be diffusion models, first part of it. And so, okay, well, what are diffusion models? So the easiest way to think about diffusion models is, or rather, we are going to look at, so diffusion models can be derived from several perspectives. We are going to look at something called variational diffusion model. I mean, there is, uh, okay, I'll talk about it. Variational diffusion model, or VDM. Okay. What is it? It is simply a Markovian HVAE with three restrictions. Okay, so we know what Markovian HVAs are. We derived the loss functions and objectives for that in the previous two lectures. Uh, but if you add three restrictions on top of these HVAs, we land on your diffusion model, particularly variational diffusion model, because all of these things are being derived from using variation techniques from variational inference and so on and so forth. Right? So what are these three restrictions? Well, first thing is the latent dimension, right? The dimension of the latent variable is equal to the data dimension. Data dimension. That's the first restriction. So if you have an image, the latent variables or the latent vectors are also going to be of the same size as the image. Okay. Second restriction is that the the latent encoder latent encoder is uh is is not learned. Is not learned. Okay. It is it is predefined. It is predefined as a sorry, as a linear Gaussian model. Okay. Or you can think, or in other words, you can say that the encoder itself is a stochastic encoder. Okay. It is it is not learned, but it is a stochastic encoder, or in other words, you can think about it as follows, right? That at each step, the latent vector is centered around the previous step's latent vector with some scaling and some variance, and that's it. So you can think about it like this: that let's say you are at time xt, and the previous latent was xt minus 1, so the encoder is going in this direction, right? So uh, you can think that your xt is actually coming from a distribution, like a Gaussian distribution, okay, which is like centered around xt minus 1 and some with some variance, sigma square, something like this. Something like this is happening, okay? So you can see why I'm calling it. So there is nothing to learn here because these parameters A and sigma, these are predefined. You'll see what these are. However, I mean, it's not deterministic either because sampling from a distribution is not a deterministic process. You have to basically, I mean, there will be some stochasticity involved when you sample from this distribution, right? So it's not a learnable yet stochastic encoder, okay? And the third restriction is, uh, uh, it is related to the parameters A and sigma here. The parameters, the parameters of the latent encoder, which is nothing but a stochastic encoder, just Gaussian maps, vary over time, vary over time in such a way, in such a way that the distribution, the way that the distribution the latent of the latent at final step, capital T, is standard Gaussian. Standard Gaussian. So what do we mean by this thing? So you think about it, right? So you are starting from x naught, you are going to x1. Okay, now x1, so x1 is going to be sampled from some ax naught, comma sigma 1 square, something like this, right? Now here from this you are going to go to some x2. X2 is going to be like something like Gaussian a, let's call it a1. This is a2 x1 comma sigma 2 square, something like this. So on until the last step, right? Xt, which is going to be sampled as Gaussian a t x t minus 1 comma sigma t square, something like this. Okay. So now, but we are saying that this distribution should be exactly equal to Gaussian 0 comma I. This is what we are saying. So this is something which is not trivial. I mean, see, if you keep adding noise, I mean, eventually it will become some noise. I mean, that is something that you can take for granted. Okay, like, yeah, sure. If you keep adding noise to your data, I mean, eventually the corruption will be enough for you to not be, I mean, the corruption would be enough for you so that you cannot distinguish between a Gaussian 0, 1 noise and the whatever noise you have generated. But that if you keep adding noise non-trivially, I mean, sorry, if you keep adding noise without keeping any restrictions, this thing is not guaranteed. Okay, I mean, uh, I hope that's clear that this distribution to be equal to Gaussian 0, 1 is something that you need to make sure. So you need to make sure that this happens by construction. It won't happen on its own. Okay. So that is why this third restriction, that the parameters, these A1, A2, sigma 1, sigma 2, so on and so forth, these parameters have to be decided in such a way that eventually at the end, this thing is nothing, this distribution is actually standard Gaussian. Uh, So these are the three restrictions. When you put it on top of your Markovian HVA, you basically come to your diffusion models or variational diffusion models. Any questions here?
Yeah, so I could not understand the first and the third condition. So in the first
Okay.
condition, what does it mean to have the latent dimension equals to the data dimension? Does this mean that we would be having, I mean, those many latent variables? Depending upon the dimension of the data.
No, so can you recall what are VAs, right? In VAs, you had an encoder and you had a decoder, right? E
Yes,
and D, something like that. So if your data was, for example, some image, right? Your latent vector is usually just a vector. So this is like R, maybe n cross 3, right? N cross n is height and width, and 3 is the number of channel of the image. And this dimension was like something called RD cross 1. That's all. And after decoding, you again get an image, which is again some R n cross n cross 3. This is how the VAs were, right?
yes,
And in VAs, this is what we called as the latent vector, right? Now,
yes,
if you see the dimension of the latent vector is RD cross 1, whereas the data of the data is n cross 3, isn't it? If
yes,
I want if I want to show you in terms of the PGMs, you have X and you have Z, right? This is your encoder, this is your decoder, right? And here this Z belong to some R D cross 1, and here X belong to some R n cross 3, something like this. So even in this, from this perspective, these two dimensions are not matching, isn't it?
yes, not matching.
Yes. So what the first assumptions for here is telling you is that, well, you have some x naught, x1, so on. So you go from here to maybe there is another x2. You go keep going something like xt. So right, all of these. So what the first assumption is telling you is that, well, all these xi's, right? All these xi's all belong to our maybe if it is an image, it's n cross 3, or something which is same for all of these x1, x2, x naught, all of these things. So, so if it is so you can think about it like this, right? That if x naught is an image, right? If it's an image, x1 is again an image, but maybe a noisy version of the image, something like this. X2 is again an image, but even more noisier than x1, something like that. So on and so forth. So it's does that make sense?
Yes, but then what's the meaning of the matching of the dimensions then?
That so this is what we mean by matching of the dimension, right? So all xi's will have same dimension, R n cross 3.
Okay, okay, okay. Yes.
Okay.
And what about the third one? I mean, wherein we are applying the normal distribution over all the latent variables. So, I mean, how is that possible that we apply the normal distribution n number of the times or many times, and eventually we
Mm.
come up with the normal distribution again?
Yeah, so this is not I mean it won't happen on its own. That is what I said, that this is something that we have to make sure happens. So we'll see that these these parameters A1, A2, so AT, all of these things are designed in such a way that eventually your final distribution will become Gaussian 0, 1.
Oh, I see. So then what
So
is the precise and the single line definition of the terms encoder and the decoder is? I mean, how do we tell the definition of these two components to a layman?
okay, so you can say that encoder is actually just a noising process here, in the sense that you're just adding noise to your data. That's your encoder.
Okay, okay,
And your decoder is your denoising process, which is starting from a complete noise. So once you make sure that the final distribution is Gaussian 0, 1, if you want to generate a new image, you can start from Gaussian 0, 1 and denoise it for these many steps and eventually get to a new data point.
Yes, so yeah,
That's your
because I,
decoder.
yes, because I asked this question in the yesterday's lecture also, that how many times, I mean, this forward and the backward process will continue, because
Mm,
we are noising, I mean, we are including noise in the original data, and
mm,
then eventually then we start the process of the denoising to get the data
mm,
back. So how many
mhm.
times we repeat this forward and the backward process, I mean, for a system?
There is no repetition involved here. So see, all of these things, so your decoder eventually here will be some denoiser, right? Some d theta. And you want to learn this theta using the loss objectives that we derived here, right? This loss
Yes,
objective.
yes,
So we just need to make sure that we are able to sample. So for example, this last term here, right? This last term demands us to sample from qxt given x naught, right? And then plug it into this equation and uh, use this to back propagate and learn theta, right? So there is
yes.
so essentially there is nothing. I mean, there is no repetition involved here. You just come up, calculate this term like so just calculate this expectation, calculate this term, back propagate. That's it.
So from whichever neural network we are learning, I mean these thetas must be running,
Uh-huh.
must be using multiple number of the epochs, isn't it? So
Yes.
so will
So
that be
no, so that
sufficient as
so
repetition?
no, so the number of epochs is sufficiently large. I mean, that's not something that you would. I mean, just I don't. I mean, so actually, I haven't trained a diffusion model from scratch. Okay, but I mean, usually you train it for a large number of time until you are satisfied with the quality of image that is being generated. Yeah.
Okay,
I
okay.
think so. I think the confusion is here that how while training, how many times do you go forward and backward, right?
Yes,
But
yes, yes.
actually there is no going forward and going backward actually. I mean, if you think about it, this is just one term that you have to calculate, right? And calculating this term just needs you to sample from xt. So once you know x naught, you just need to do some reparameterization and obtain xt, plug it into this equation, and simply backpropagate it. That's all.
Okay, okay. Now
Maybe
I
it
have
will become maybe it will become little clear when we actually derive simplify that term and see what it brings. Yeah,
okay, fine.
you're right. Okay, so let's start with the first assumption that we said here. Okay, not the first assumption. So it's the second assumption, right? That what does it mean? That so this is what it means, right? So the second assumption is telling us that latent encoder is not learned. It is not learned. Okay, it is predefined. So we are going to predefine it as a linear Gaussian model. So basically, what it means is that your encoder, which is stochastic, okay, what does that look like? So this basically means that you're given at any point xt, given xt minus 1, okay, this distribution is just a Gaussian distribution, okay, of xt. What are the means and variances of this Gaussian distribution? Well, here is where the parameters will come in. So alpha t is a parameter, root alpha t xt minus 1, comma 1 minus alpha t I. This is how the encoder is defined. So you can think about it like this, right? So from x naught, you have a distribution q of x1 given x naught, right? You sample from this and you obtain x1. Okay. Now you have x1. So you can now, you know the distribution q of x2 given x1 and sample x2 from it. And do this until xt, which is q of x capital T given x capital T minus 1, something like this, right? So this is the nature of your stochastic encoder. Here, alpha t's are basically your parameters. Okay. Uh, okay. So Sometimes people also write this distribution as equal to Gaussian xt of mu t of xt, so the mean parameter, and sigma t of xt, the variance parameter. Okay, the mean parameter mu t of xt is nothing but uh, it's nothing but root of alpha t x t minus 1, right? And sigma t of xt is nothing but 1 minus alpha ti. Okay, this is just another way to write the same thing. That's all. Nothing fancy, just a fancy way. That's all. Anyway, okay, right. So if this is the case, right? So basically we have this equation that xt is being sampled from. So if you want to sample xt, it will come from q of xt given xt minus 1, which is normal of xt with parameter alpha t xt minus 1, comma 1 minus alpha ti. Okay, this is what you have. This is your encoder. So what you can do now is, so what if I want to sample from this distribution? So if you want to sample from any Gaussian distribution, the first thing that should come to our mind is the reparameterization trick, because that is the easiest way to sample from any Gaussian distribution. What does that mean? Well, what you can do is you can write xt as your mean, which is root of alpha t xt minus 1 plus square root of the variance 1 minus alpha t times epsilon. Okay, maybe write it as epsilon. Okay, where epsilon is coming from Gaussian 0 I. I mean, this is the basic reparameterization trick if you want to sample from any given Gaussian distribution. Nothing fancy, right? Now, similarly, what you can do is you can write xt minus 1 similar. So because this is a like a, I mean, if you change t to t minus 1, what would be xt minus 1? Xt minus 1 would be root of alpha t minus 1 xt minus 2 plus square root of 1 minus alpha t minus 1 epsilon, where epsilon is again coming from Gaussian 0 I, right? Nothing fancy. I'm just writing down the equation. So what you can do is you can recursively, so now you can substitute this in this equation. Okay. So what does that mean? So this implies that, so, okay. So xt is basically what? So if I can write basically xt in terms of xt minus 2 instead of xt minus 1, right? So this will be what? Root of alpha t. What is xt minus 1? I will substitute this equation here. Square root of alpha t minus 1. Uh, Maybe call it uh, let's call this x epsilon t minus 1, just to be clear that there are two epsilons, right? So this will be root of alpha t minus 1 x t minus 2 plus square root of 1 minus alpha t minus 1 epsilon t minus 2 plus square root of 1 minus alpha t epsilon t minus 1. This is what it is, right? So I have done nothing. I have just taken this equation, I have substituted it here. That's all. So let's sort of simplify this. So this thing will become what? So basically, I will take the noise terms on one side and the rest of the terms on the other side. So this will become square root of, so become square root of alpha t minus 1, right? X t minus 2, okay, plus square root of alpha t, uh, square root of alpha t into, so this is 1 minus alpha t minus 1 epsilon t minus 2, okay, plus square root of 1 minus alpha t epsilon t minus 1, right? Uh, I hope this is clear that I have done nothing. I'm just simplifying things. Now,
Uh, But then from
Yeah.
where do we get, I mean, all these alphas and I mean, what is the rationale
Yeah.
behind considering this xt as a normal distribution of a particular form?
Yeah, that will come to that. So we'll see the effect of these alphas. So alphas are actually very important. We will talk about it in detail because that is sort of important. Yeah. So now what we can do is see these two are so okay. Let me highlight these two things perhaps, right? So if you look at it, the epsilon t minus 1, t minus 1 and epsilon t minus 2, these are both Gaussian 0 I, right? And we have a linear combination of these two standard Gaussian random variable. So what we can do is we can write them in terms of a single Gaussian random variable uh, just by using properties of Gaussian random variables. So actually this can be written as square root of alpha t minus 1 x t minus 2 plus. So I mean if you have ax plus by, right, where x and y are both Gaussian, this is identically distributed as square root of a square plus b square times z, where z is again another Gaussian random variable. But this is, I mean, do you know this result? Uh,
No, no.
okay, so and it's a okay, uh, okay, so maybe we can do is can sort of give you a short proof here. So let's say that x comma y comma z all are normal 0 1. Okay, and you have a new random variable t, which is ax plus by. Okay, so there is a property of Gaussian random variables that linear combination of two Gaussian random variables is again Gaussian. Okay, however, we don't know what will be the mean and sigma of this random variable. So what you can do is to calculate the mean and sigma. So mean is nothing but your expected value of t, right? That's the first moment. So that will be equal to a is a constant, so a times expected value of x plus b times expected value of y, right? This and now x and y are, remember, they are zero mean Gaussian random variables. So expected value of x is 0 and expected value of y is 0. So this is just 0. So mu is 0. What about sigma square? So sigma square, that will be equal to variance of t, right? So variance of t. Now, what is the variance of t? So there is a, sorry.
Yeah. So that will become
So
variance of
yeah,
this. A square
yeah.
plus
So
B
variance
square.
of this. So this is a square expect variance of x plus b square variance of y plus so I think it's 2ab, not
Covariance of
mean
AX and B.
2ab times covariance of x and y. But x and y here are like okay, I didn't mention it, but they are IID. So the covariance term, this thing is 0. So this is just a square variance of x is just 1. So a square times 1 plus b square times 1. This implies that sigma is nothing but square root of a square plus b square, right? So, so for this holds true for Gaussian random variables, okay? So I'm just using that property that mean uh, will be unaffected because mean is still 0. But however, the variance will become square root of sum of variance, like I mean this result basically. Okay, is that clear?
Yes, yes.
So yeah, so what you can do is uh, right. So here we are, right? So we have a similar situation here. You have two Gaussian random variables that are ID, and you have a linear combination of them, and you want to write them in terms of Okay, so okay, one point that I missed here is so basically T is a random. So from this result, what we can say is that T is a random variable with zero mean and a square plus b square variance, right? This is what we derived here. So we got mu and sigma square. So what you can write is T is actually again by reparameterization trick. What you can do is so it's zero mean, so zero plus square root of a square plus b square times z, where z is another random zero mean like standard Gaussian random variable, right? So this means t is equal to square root of a square plus b square z, right? Um, so I am just using that property here uh, that there are two Gaussian random variables, epsilon t minus 2, epsilon t minus 1, right? And both of them are IID. And we have a linear combination of these two. So I can write them as square root of, I mean, I'm just using that result that I just stated, right? So we remove this plus square root of, so the square of each of these, right? Square root of alpha t into 1 minus alpha t, square root of this square plus square root of 1 minus alpha t square, right? And let me call this epsilon t minus 2. Maybe what I can do is let me call this star. This is again star. These are all stars. These epsilons are star. Okay. I'm just doing that to just avoid some confusion. That's all. So, and this is so epsilon stars are just Gaussian 0, 1, and I am writing them as this thing. Is this fine? Like I'm removing the star now. This is just epsilon t minus t is again just epsilon t minus 2 is just again another Gaussian random variable, IID, Gaussian random variable. Is that fine?
Yes, yes.
Okay. So what have we derived? So this is what alpha t minus 1 x t minus 2 plus square root of this is what? So this is alpha t minus okay. Well, I think I missed something. So this is alpha t minus 1. Yeah. Alpha t minus 1 plus 1 minus alpha t, right? Times epsilon t minus 2. So alpha t gets cancelled out. And this becomes square root of alpha t minus 1, right? X t minus 2 plus square root of 1 minus alpha t minus 1. Okay? Epsilon t minus 2. And this is x t. Is this clear?
Yes.
Okay. So now what I can do now is again replace xt minus 2 in terms of xt minus 3, right? I can like go recursively now. So what will it become? So I actually you can find a pattern. You can do it for xt minus 3, but maybe do it as an exercise, but I will just tell you what it will become eventually. So if you do keep doing it recursively till x naught, what will this thing become? So this will become product of alpha i's, right? I going from 1 to capital small t, x naught plus square root of 1 minus product of alpha I is again I going from 1 to t epsilon naught. This is what xt will become in terms of x naught. Okay, this is in terms of x naught. And what so these product of alpha i's we call them alpha bar. Okay, so this is alpha t bar uh, times x naught plus square root of 1 minus alpha t bar epsilon naught. Okay, where epsilon naught is like some Gaussian 0 I. Okay, xt. So now from here, what you can say is that this is again actually a Gaussian random variable, right? Because epsilon naught is a Gaussian random variable and you are just scaling and shifting it. So this is a Gaussian random variable of xt. And what is the mean? The mean is square root of alpha t bar x naught. And what is the variance? The variance is 1 minus alpha t bar I. This is what the distribution of xt is in terms of x naught. So this distribution is often called as q of xt given x naught. Any
Okay,
doubts still here?
yeah. So this is the same thing. I mean, we discussed in the yesterday's lecture that Q
Yeah.
function. Okay.
Yes, yes. So if you look at it, here we have a q function q of xt given x naught. So I mean, so you see, though we have defined our process in a Markovian manner, in the sense that you can only calculate x2 if you know x1, because that is defined. That is how this distribution is defined. But you can actually simplify and write any latent vector in terms of x naught directly.
Yes.
You just have to do this reparameterization. Take a Gaussian random variable and do this reparameterization. That's all.
Yes. Can there be a, I mean, simple explanation of this fact that what could be, I mean, what speciality of an encoder it
Mm.
refers to that just from a point, I mean, we can reach to any other point. An
Sorry,
intermediate
can you
point.
repeat your question?
So, I mean, which speciality of the encoder this
Mm.
fact refers to that from x not only, I mean, we can reach to x5 or we can even reach to x20 and without
That is
considering any.
actually because of the Gaussian distributions, actually. Because of this Gaussian assumption that the transition kernel is actually a Gaussian distribution, we are able to write any xt in terms of x naught directly.
Okay. And
This is
in generative modeling, how common such a distribution is because apart from the normals, quite possible that in few specific domains, the distribution may not be that much normal.
so actually, mm, well, I think there is one paper, something called cold diffusion, if I am right. Yeah, maybe you can have a look at this paper. So this is one paper that did exactly this thing, where they sort of they showed that, well, you need not. So this is like a noising forward process, right? That you are adding noise at each time step. They showed that, well, you can actually learn diffusion models with any arbitrary transform. It need not be a noising process. Yeah, you can have a look at this paper. Perhaps that should perhaps give you some idea if you're
Okay.
interested. But nonetheless, Gaussian distributions are quite ubiquitous. I mean, those are like, I think more than easy to work with, they are computationally, it's very easy to process them. Yeah.
Yes, yes, yeah. Fine. Thanks.
Uh, Okay. Uh, okay. So one thing to note perhaps here is that, well, so yeah, so let's look at this point, right? Something that something in s- something that is related to your third assumption, right? So what is xt, x capital T? This will be distributed as Gaussian, right? X P, x capital T, right? Square root of alpha capital T bar x naught, comma 1 minus alpha T bar I. And we want this distribution to be equal to what? We want this distribution to be equal to normal x t 0 comma I, isn't it? Uh, that's right? I mean, this is what we want from the third condition. Also, uh, okay, let's look at x1, right? X1 is again another Gaussian distribution centered around, oh, sorry, this is x1 square root of alpha 1 x naught 1 minus alpha 1 I. I mean, let's, for the sake of argument, okay, for the sake of argument, let's say that, I mean, x1 is approximately equal to x naught. Approximately. I mean, this it's not exactly equal to x naught, but I mean, like since you are on the first step of your Gaussian process, like the noising process, the noise is not very much visible. Okay, this is just for the sake of argument, right? So in that case, what do you want this distribution to be equal to? You want this distribution to be equal to Gaussian x1 with mean exactly x naught and zero variance, right? Like zero. That's all, isn't it? I mean, like a Dirac delta at x naught.
Yes.
This is just for the argument's sake. I mean, like strictly speaking, this is not correct, but I'm just trying to get an intuition of these alpha t's, alpha i's, so on and so forth, right? So what does this tell us? So this tells us that, well, from the first, let's call this some first equation, let's call this second equation. From one, what do we, so okay, so from one, what do we know? We can say that, so when square root of alpha t bar x naught, this should be equal to 0, right? And 1 minus alpha cap, this is capital T, this bar should be equal to 1, or just, yeah, just 1, okay? And so what does this mean? This means that square root of alpha t, or you can just say that, so both of these conditions, what do they imply? They imply that, I mean, if you think about it, this implies that alpha t bar should be equal to 0, right? And if alpha t bar is equal to 0, then this also holds true. So, I mean, both of these conditions tell you that product of alpha t, like alpha t bars are defined as follows, right? Alpha i's, I going from 1 to capital T, this should be equal to 0. This is what this first condition implies, right? What is the second condition? The second condition tells us that, well, it tells us that, well, square root of alpha 1 x naught should be equal to x naught, and 1 minus alpha 1 should be equal to 0, right? What does this mean? So this can happen if alpha 1 is equal to what? Just 1, right?
Yes.
Is this fine?
Yes.
Okay.
Yes.
So this is something interesting. So basically alpha i's are such that, well, alpha 1, so in the beginning, the alpha is 1. Okay. So if you think about it, so maybe it is going to some time step t, right? And this is the value of alpha. So at the first time step, at time step t equal to 1, this has to be equal to 1. Okay. I mean, it is at least it is close to 1. Okay. But when will this thing happen? The products will should vanish to 0. When can this happen? So if the product of the numbers, like these real numbers, is going to 0, when is that possible? That is only possible if alpha i's are, so like alpha i's slowly goes, like slowly become 0, right? I mean,
Fractional values, if we keep on multiplying, say the large number of the fractional
no,
values,
so,
then
so
it
so
would
so
be.
you're doing it. So there are two things. So first thing is that, uh, so one thing is that either alpha I should just one of the alpha i's should become 0. In that case, the whole product is 0, right? In the
Yes.
other case, but that is not, um, I mean, that we don't want that. I mean, if you are setting alpha i's to be equal to 0, then you are actually just sampling from Gaussian 0, 1 actually. If you think about it, if alpha t bar becomes 0, then this becomes 0 and this becomes I. I mean, at any time step, you cannot just randomly put it to 0. The other way is that you keep multiplying like small fractional values for a long time, right? In that case, it will become close to 0, right? So, so the first thing, so to satisfy this condition, alpha i's should slowly go down to 0, okay? and t should be large enough, right? So, I mean, it could look like a function, something like this, right? Where it is starting from 1, but it's slowly going down to 0. Or it could also look something like this, maybe. Something like this. Could look something like that. You can, so this is how you can design your alpha is. You can choose it to be any of these functions. You can also choose it to be a linear thing, right? Where at the end it becomes 0. Uh, I don't know. Is that making sense? Does this argument make sense?
Can you repeat this argument? Yeah.
Okay, so what I'm saying is that uh, alpha 1 has to be close to 1, so it is starting from here, okay?
Yes.
But the product of alpha I should be close to 0 or should be small enough, right? Now, when is that possible? That is possible if first alpha i's are slowly getting close to 0, right? They are fractions, okay? But
Yes.
I mean, you are multiplying these fractions for a finite number of time, t, capital T
Right.
number of times, right?
Right.
So if you, so if t is small, the product of alpha is won't go to 0, right?
Correct.
You need to multiply these things a large amount, like a multiple times, a sufficiently large amount of time, so that these fractions get multiplied multiple times and become 0 or small enough.
Yes.
So for that reason, it has to become small at t. It has to be 1 at 1. Okay. So what kind of schedule? So if I write alpha as a function of time, right? How should the graph of alphas look like? That's the question. So what I said was you can have any function which is monotonically decreasing to 0 between 1 and t.
Right.
So this is how you can choose your alphas. Like that is what you asked, I think, right? That how should we choose the alpha? How will we make sure that the third condition holds true?
Right.
So this is the answer to that question, that you can choose something like this, alpha you can make your alpha to follow something like this, and yeah, you will get what you want.
Yes. Yes. Yeah.
Okay, now let's get back to business. Okay, so uh okay. Oh, wait. Yeah. Okay, so let's go back. So okay, everything is fine till now. We have understood the forward process, right? We have understood this direction of the diffusion models, this direction, the forward direction. We know how to calculate any latent at any time if you know x naught. Okay. We have also understood, or we have an idea of how the alpha t's should be chosen so that the third assumptions hold true. Okay. All of those things are fine. But what is of our interest, the thing that is of our interest is the reverse process, right? Which is what we are going to learn. I mean, if you want to generate new data point, you're going to start from some noise and you are going to run the reverse process. Uh, uh, that is what we want, right? End of the day. And for that, we have seen this thing, right? Uh, we have seen this weird looking, actually, it's not weird, it's quite beautiful. It's quite intuitive, this equation. So this is going to be our learning objective, right? This is our learning objective. Okay. Now so I mean your reverse, so okay. So the reverse process or the generative process, we have to learn that. So we are going to learn a denoiser, maybe some d theta, okay? Using this loss function, this L2 loss function. Is that fine? Does that make sense? That I mean, that is what we have been, that is why we did all the HVAE derivations, because this diffusion model is also a HVAE, and we can learn any HVAE using this loss function. Is that fine? Does that make sense? The next
Yes.
step.
Yes.
Okay. So now, okay, how much? Okay, so maybe in next some few minutes, what we will do is, uh, so okay, let's analyze this equation, right? So P theta x naught given x1 is fine. This is like a reconstruction term. So what is of our interest is, well, so first of all, something that is not very clear to us is this distribution. Remember the trick that we did to like derive this alternative loss function, where we instead of conditioning on xt minus 1, we conditioned xt on both xt minus 1 and x naught, and that led us to this distribution. So what is this distribution for our setup? Like, for example, what I mean by that is, we know that q of xt given x naught is what? We know that this thing is nothing but this Gaussian, uh, we know that this is nothing but Gaussian xt square root of alpha t bar x naught, comma 1 minus uh, alpha t bar I, right? This is what it was. Yeah. So we know this thing. So using this thing, can we derive what is q of xt minus 1 given xt comma x naught? This is what we want to derive. So because only when we derive this term, we will be able to calculate the KL divergence, isn't it? So so
Yes.
let's so let's first derive this. What is this distribution? So we want to find what is q of xt minus 1 given xt comma x naught. Okay. Okay. Well, this distribution, we will again resort to. So whenever you want to find something, write it in terms of what we know. Okay, that is the first step, sort of. And that's the thumb rule. Should always write something we want to find in terms of what we know. So to do this thing, we'll resort to again Bayes rule. That's our go-to method. That's the only thing we know basically. Okay. So we know all the distributions where this t is greater than whatever the argument here is, right? So we'll do that. So this is equal to q of. So I'm using Bayes rule to write this thing down. So q of xt minus 1 comma x naught, q of xt minus 1 given x naught divided by q of uh, xt given x naught. Yes. Is this fine? I'm just writing it as Bayes rule. This is like
Yes.
p of x given y is equal to p of y given x into p of x, right? Divided by p of x, right? So this is p of
Yes.
y given x. This is p of x. This is p of x given y. This is p of y, right?
Yes.
Okay. So now, actually, you know all the terms here. All the terms here, we know all of them. That's the beauty of having this Gaussian encoder, right? Because of the Markovian assumption, right? This thing is nothing but q of xt given xt minus 1 because of the Markovian assumption, right? The second term is as it is q of xt minus 1 given x naught divided by q of xt given x naught, right? Okay. So now let's not worry about the so all of these are Gaussian, right? This is Gaussian with what is the mean? Xt given xt minus 1, right? So remember we have this Gaussian kernel, right? Where is it? So yeah, this thing. Yeah, this thing. So it's root of alpha t times, wait, what is it? Root of alpha t xt minus 1. Okay. This is root of alpha t xt minus 1, comma 1 minus alpha t I, right? This is the first term. What is q of xt minus 1 given x naught? Well, that also we have derived, right? Uh, yeah, so this from this equation, this is nothing but Gaussian xt minus 1 given x naught. So that will be root of alpha t minus 1 bar x naught, comma 1 minus alpha t minus 1 bar I, right? Divided by what is the this term? So the denominator is similar to this thing, but for t, xt, right? So that is Gaussian square root of alpha t bar x naught, comma 1 minus alpha t bar I. Okay. I hope this is clear. Nothing fancy. I've just written down the equation, like the distributions.
Yes.
Right. So what we will do is, so instead of writing the whole Gauss, so what we will do is, instead of writing down the normalization term, so there is 1 by 2 pi sigma thing that comes in the denominator, right? We'll ignore that. Instead, what we'll do is, so whenever you're working with Gaussian, just worry about the terms that are inside the exponential. That is all you need to really worry about. So maybe I'll explain it, like illustrate it. So for the first term, what will be the term inside the exponential of the Gaussian random variable? That will be something like minus x minus mu whole square by 2 sigma square, right? That is how it is, right? So what will it be? So this is for xt, right? So this is xt. What is the mean? The mean is square root of alpha t xt minus 1, right? Divided by 2 sigma square. What is the 2 sigma square? This is 1 minus alpha 2 into 1 minus alpha t. Is this fine? I have just written the term that will be an exponential for this distribution, the first Gaussian.
Yes, x minus mu
Oh,
and this
whole
everything.
square.
Yes, square.
Yeah. Sorry, yeah, right. What will be the second term here? So the negative is already taken outside. So I can write it as, so this is x for xt minus 1, right? So it's xt minus 1 minus, what is the mu? Mu is square root of alpha t minus 1 bar x, sorry, x naught whole square divided by 1 minus alpha t minus 1 bar, right? 2 times this thing. Okay. Plus similarly just for xt minus square root of alpha t bar x naught whole square divided by 2 times 1 minus alpha t bar. Is this fine? I have just written the 3 terms that
Yes.
are of our interest. Nothing fancy. Okay.
And
Now,
addition, subtraction symbols are fine. I mean, first minus and then second term should be
so the
okay.
minus is taken outside of this bracket. These brackets are taking care of the minus sign outside.
Yes. And yeah.
Let's not worry about the normalizing constants.
Okay.
Like
Okay.
normalizing constants, you can always derive the normalizing constant after figuring the numerator, right? Because the normalizing constant is nothing but integration of this. That's all. So
Yes.
okay, if we have this, let's write it down a little more clearly. This is so exponential. uh, Okay, maybe I should write it a little carefully. So this is exponential of minus. So I will take the 1 by 2 outside, right? Minus 1 by 2. Uh, First term is xt. Again, I'm writing the same thing down. So xt minus square root of alpha t x t minus 1 whole square by 1 minus alpha t plus xt minus 1 minus square root of alpha t minus 1 bar x naught whole square divided by 1 minus alpha t minus 1 bar plus xt minus square root of alpha t bar x naught whole square by 1 minus alpha t bar, close the bracket. That's it. So I've just written it a little concisely. That's all. Okay, so what we will do now is, well, there's nothing to do. We'll simply expand the square terms, like whatever is there in the numerator, right? We'll just expand those. Okay, another thing to note here is that this is a distribution of xt minus 1, okay? So so we only need to concern ourselves with the terms that are related to xt minus 1. The other terms will again go as constant, right? Does that make sense? Like in this distribution, we only need to worry about the terms which are related to xt minus 1. Other terms that are related to, for example, xt, x naught, those are just constant because they are conditional. This is a conditional distribution. Does that make sense?
Yes, yes.
Okay, so what we can write down this, so this thing is equal to exponential of minus 1 by 2. Okay, this is what? The first term here is xt square plus alpha t xt minus 1 square plus 2 square root of alpha t xt minus 1 xt, okay, divided by 1 minus alpha t, the first term. What is the second term? The second term similarly is xt minus 1 whole square plus, oh wait, it's a minus, a minus b. Okay, wait, uh, this will be a minus somewhere. Okay, so the second term will be xt minus 1 whole square plus alpha t minus 1 bar x naught whole square minus 2 square root of alpha t minus 1 bar x naught x t minus 1 divided by 1 minus alpha t minus 1 bar. And this third term is just dependent on xt and x naught, right? So we can just write it as some constant of x naught and xt. Is this fine? So I've just expanded the square terms, and the third term here is of not of our interest because this distribution is pertaining to xt minus 1. So we only need to consider the terms that are related to xt minus 1. Third term is just a constant for us. We need not worry about it.
Yes, yes, yes.
So once we have some constant, we can again use like discard this term, right? I mean, we need not worry about the constant terms. We just need to worry about the terms that are going to influence the exponential. So this is again exponential of minus 1 by 2. So we need to only worry about this term and this term, the first two terms, okay? That's all. Okay, so wait. So if that is the case, then what we will do is, so we'll take the minus half inside, okay? Uh, do we take the minus half inside? Or should we wait? Uh, let's wait. Let's see what happens. Okay. So okay. Okay, actually, if you think about it, there are other terms that are also dependent on xt and x naught, right? For example, okay, maybe I should write it down very explicitly. So this xt is again not of our interest. This x naught term is again not of our interest. This term has xt minus 1, this term has xt minus 1, this has xt minus 1, this has xt minus. So these terms are of our interest. Okay, so what we can do is these two things can also be subsumed in this constant term. Is that fine? So I mean, whatever is whatever thing whatever term does not involve xt minus 1, just ignore them. That's all. So that will become minus 1 by 2. Uh, now let's write it down. So let's write it down. So this will be minus 2 square root of alpha t x t minus 1 x t divided by plus alpha t x t minus 1 whole square divided by 1 minus alpha t. That's the first term. plus minus 2 square root of alpha t minus 1 bar x naught xt minus 1 plus x t minus 1 whole square divided by 1 minus alpha t minus 1 bar. Okay, so I have subsumed everything in this constant C, and I have used this proportionality sign. Remember that I am using proportionality. I'm not saying it is equal because constant is just a norm, like just a scaling factor. We can ignore that. Okay, now let's see what else we can simplify, right? So there are two terms here, one with xt minus 1 square and other with xt minus 1. So let's club them together. That will become 1 minus 1 by 2. What will be with xt minus 1 square? Okay, so with xt minus 1 square, we have the first term is nothing. Okay, so this is nothing but alpha. The first thing here, so it's alpha t, right? So it's alpha t over 1 minus alpha t plus 1 over 1 minus alpha t minus 1 bar, close bracket xt minus 1 whole square, right? Okay, in the second term, we have minus 2 that is common. So this is minus 2 here, that's common. Uh, Rest of the things, I don't think anything is common. So there, let's take things out. So that will be root of alpha t xt, root of alpha t xt divided by the denominator there, that was 1 minus alpha t plus, what is the thing here? Square root of alpha t minus 1 bar x naught divided by 1 minus alpha t minus 1 bar bracket close xt minus 1. Okay. So just some simplifications. I'm just doing some simplifications. That is all. Okay. Is this clear? Like, is this fine? Uh,
Yes, and how could you bring this x t minus 1 square outside this thing? 1 minus alpha t is fine.
so this is like this, right? So you have alpha t over 1 minus alpha t here. That is here, right? And there is 1
Yes,
over 1 minus alpha t minus 1 bar here. That is coming here. And I am taking xt minus 1 square outside.
yes. Now I understood. Yeah, fine.
Yeah.
Thanks.
Okay. Now what else? Now what do we do? So basically we will do something like completing the squares. That's all. Let's do that. So this is so okay. Now a little bit of calculation is involved. I am going to do it nonetheless. Okay. That is exponential minus 1 by 2. Uh, so this is alpha t. Yeah, let's do it. This is so the if you sum these two, what will it become? So this is alpha t 1 minus alpha t uh, bar, right? Plus 1 minus alpha t. That's all divided by 1 minus alpha t 1 minus alpha t bar into xt minus 1 square. So I have just added these two fractions. That's all. Uh, okay, minus 2 times minus 2 times. Should we do anything here? Okay, nothing required. So let's keep that as it is. That is root of alpha t xt divided by 1 minus alpha t plus alpha t minus 1 bar. It's not divided by 1 minus alpha t minus 1 bar. Xt minus 1. Okay. Uh, Again, just simplifying things. This is equal to exponential of minus 1 by 2 So this will become what? So this will become what? So this is equal to alpha t minus alpha t bar plus 1 minus alpha t, right? So alpha t gets cancelled out, right? Uh, oh, this is alpha t minus 1 bar actually, alpha t minus 1 bar, right? That is what it was. Yeah, so this is alpha t minus 1 here, alpha t minus 1. So this will become 1 minus alpha. So this will become, so this is equal to actually 1 minus alpha t minus 1 bar. And what is alpha t minus 1 bar? That is just product of alpha I going from 1 to t minus 1, right? That is how we had defined it. So if I multiply it with, so so if I multiply it with alpha t, this will become nothing but alpha t bar. Is that clear? Uh,
How did you
okay,
speak?
so okay, I'll write it down. So that thing, so I hope this is clear, right? That is equal to 1 minus alpha t minus 1. Is that fine?
Yes,
Because this alpha t, this thing and this thing gets cancelled. Okay. Okay, how is, so this is equal to 1 minus alpha t product of alpha I going from 1 to t minus 1. Is that fine?
yes, yes,
This is equal to 1 minus product alpha I going from 1 to t, because
yes.
you can take this inside. And this is nothing but 1 minus alpha t bar.
Oh, yes,
That fine?
yes, yes,
So so I can just club those two and write it down as this is nothing but 1 minus alpha t bar divided by 1 minus alpha t, 1 minus alpha t bar, right? Oh, sorry, this is t minus 1. This is t minus 1. Okay. Into xt minus 1 whole square, right? Minus whatever the term here was. Maybe I'll just copy paste it to save some time. Just copy, paste. Is this fine? I have just I am just simplifying the xt minus 1 square term. That's all.
yes,
This is what we have got till now. Okay. Okay. Now what we are going to do is we are going to take something common. This will be exponential minus 1 by 2. Okay. I will take, so whatever this term here is, right? I will take this common out of both the terms. So I will multiply, divide this term here and take things out. So maybe let me show what I mean by that. So let me take 1 minus alpha t bar divided by 1 minus alpha t, 1 minus alpha t minus 1 bar. Okay. This term outside. What will remain inside? So this will be xt minus 1 whole square because that's nothing else is there. Minus 2 times. Uh, okay, I don't have enough space here. Maybe what I'll do is I'll make this a little smaller and let me write it down. So minus 2 times, what is it? So this is, the numerator is square root of alpha t xt divided by 1 minus alpha t plus square root of alpha t minus 1 bar x naught divided by 1 minus alpha t minus 1 bar. Okay, this is the numerator. And what will be the denominator? Whatever we have taken out, right? So that will be 1 minus alpha t bar divided by 1 minus alpha t into 1 minus alpha t minus 1 bar xt minus 1. I don't know, is this clear? Like what I have done here? So I took this term common out of both the things. So there are two terms, this term and this term. I took this factor common. So since the first term already had this factor, it just xt minus 1 square remains. However, there was to take this thing common out of the second term, I need to multiply divide it by same thing. So the numerator will come out here, okay, and denominator will remain as it is. Is that fine? Or is
Yes,
there
this seems,
any?
yes, this seems to be correct. Uh, yes, yes, fine.
Okay, so this thing will become exponential of. So now it is just to simplify things. That's all. So this is 1 minus alpha t bar over 1 minus alpha t, 1 minus alpha t minus 1 bar. Okay, what is inside xt minus 1 square minus. Now, what will happen is this thing will go to the numerator, right? Like this thing will go to numerator, and this term will come here in the denominator. In so if you do that, uh, what will happen? Maybe let me write it down. Let me add the page. So so I know this could be a little difficult to follow because there's a lot of like calculations involved, but nonetheless, I think it's a good exercise to do it, to actually sit down and like derive everything. So let's just do it, okay? So this will be 1 over 1 minus alpha t bar, okay? So if I take this inside, what will happen? So see, the first term here, this term here, right? This has a denominator of 1 minus alpha t. And this thing will come here in numerator and will get multiplied here. So in that case, this 1 minus alpha t will get cancelled with this 1 minus alpha t, and this thing will, this is the only thing that will remain. Does that
Yes,
make sense?
yes, yes.
Yeah. Okay. So if you if you can follow this through, so what is this thing? So this thing is actually nothing but the first term is root of alpha t xt into 1 minus alpha t minus 1 bar. Okay. Because the denominator is now cancelled with this thing. Okay. So similar thing will happen with the second term, but the other thing will get out. So now you have this term here. These two terms will go in the top and get multiplied. This term will get cancelled with this term, and this thing will remain. This term will remain. So that will become square root of alpha t minus 1 bar x naught into 1 minus alpha t uh, x t minus 1. Is that fine? Like uh, I did skip some steps and directly wrote something. I will clearly write this thing again, but just to be sure that everything is making sense, what I did.
Yes, yeah, I'll have to do, I mean, these calculations on my own also.
Yeah.
Uh,
Yeah, I think that's a good conclusion. Yeah. So this will become so this is the final thing. So this will become minus 1 by 2. What we will do is so minus 1 by 2. So this thing we will write it as its inverse. So let me write it down. So this is 1 over 1 minus alpha t 1 minus alpha t minus 1 bar divided by, so I am just taking this thing below, okay? This is 1 minus alpha t bar, okay? This is the common term and whatever is inside. So whatever is inside. So what is inside? This is nothing but xt minus 1 square, right? The first term minus 2 times square root of alpha t 1 minus alpha t minus 1 bar xt plus square root of alpha t minus 1 bar 1 minus alpha t x naught divided by 1 minus alpha t bar x t minus 1. This is what it is. Okay. So, okay. If we have this, now we can, what we can do is, uh, okay, so, uh, now you can see basically what, so this is again resembling like a Gaussian distribution, right? So this is like exponential of a quadratic term inside, right? We just need to find out what is the mean and variance. So this is directly proportional to a Gaussian distribution of xt minus 1. But what is the mean and what is the variance? To find the mean and variance, what we will do is, it's simple. So, so this is some quadratic term. We need not worry about it. Like, okay, we need to worry about it, but hold on to that for a moment. What is the denominator here? The denominator is this thing. So if you remember, the Gaussian is x minus like this. It's x minus mu whole square by 2 sigma square, right? This is how it is. So 2 is here. This is our sigma square, isn't it? This is our
Yes.
sigma square, right? Uh, okay. And moreover, uh, so okay, so this is our sigma square. So this thing, let me just write down the sigma square term then. This thing, so one this thing, right? This whole thing. So what is it? 1 minus alpha t, 1 minus alpha t minus 1 bar divided by 1 minus alpha t bar I. This is our variance. Okay. What is the mean? So again, remember that this is x minus mu whole square, right? This thing is x minus mu whole square, right? So if you expand x minus mu whole square, it will get x square plus x square minus 2x mu, right? So 2 is here, x is here. So whatever else is here, this term, this is actually our mean, isn't it?
Yes, yes, yes.
So this is our mu. So this thing, square root of alpha t 1 minus alpha t minus 1 bar xt plus square root of alpha t minus 1 bar into 1 minus alpha t x naught whole, this whole thing divided by 1 minus alpha t bar. So maybe you can see that this is your mu q of xt comma x naught. This is the mean function, and this is your variance sigma q of t. Okay,
So,
so this is
yeah, yeah. So I have a query
this is
here.
your
What can
q of xt. Yeah, just a second. So this is q of xt minus 1 given xt comma x naught. Yeah, please go on.
yes, so I mean, what's the purpose of writing this xt and x0 together along with this mu? I mean, why so?
So this is mu q is a function. So this is like mu q. This is a function of xt and x naught because xt is involved and x naught is involved. So this is a function of xt and x naught. This whole thing is a function of xt and x naught.
Okay, okay, yes, fine.
Right? So this is our distribution, the whole distribution that is required for us to. Okay, I mean quite a long derivation, like quite a long thing, but this is what is so this distribution end of the day, this is nothing but a Gaussian is what we have got. Okay, this distribution is a Gaussian distribution with means with this mean, this mean and this variance. Okay, okay. Uh, I think we have I think we did a long derivation. So I don't know, like should I keep doing such derivations? Like, do you think that I can skip it, or do you think that I should do it? I don't know because might become like
Yes. So, but then, uh, can there be a balance in between the derivations which are actually required and are, I mean, essential to understand the underlying theory? Or, and then for the remaining derivations, you can just, I mean, give the reference
Mhm.
material or the handouts, whichever is comfortable.
Yeah, I can do that. Yeah, I can do that. I can do that.
Otherwise, there is no harm if you do the derivations here. Also, no issues. I mean, because in the derivation itself,
Mhm.
lots of learning is involved, and many ideas, I mean, become clear. I mean, by seeing the derivation, which otherwise would be difficult to understand.
Yeah, yeah, sure. Yeah, I agree because even while deriving, I feel that this is sort of becoming very. boring. So yeah. Nonetheless, what I'll do is, yeah, I will make a call. Maybe that's a better thing. That make a call. If things feel required, then I'll do it. Otherwise, maybe I'll just write down the result and refer you to the thing. But nonetheless, this makes things comprehensive. That is another aspect. Like once you have attended or seen the lecture, you don't need to go back to any reference material. So that is another way to look at it. But yeah, we'll see how to do it. Yeah.
Yeah.
Okay, so maybe we'll stop here today. Okay. So I think it's well over 1 hour today. Yeah, it's 1.5 hours. So uh, let's stop. Let's stop here. Uh, what we will do next time is so I mean, of course, see, whatever calculations we do, we should be very clear about what is the end goal. We did all this derivation. You can like forget if you want to forget, you can forget everything. But we did it to get this distribution, and we want to calculate this. So see these. So where this term is not at all important because I mean this does not involve theta, so this is not going to bother us. This thing is nothing but a reconstruction term. This will become we'll see that this is nothing but a reconstruction term, so we did not need not worry about that as well. We only need to worry about this term, and this is where we all of these things are going. Okay, we saw what our encoder is, we calculated what this distribution should be using our encoder. We will see how to calculate what will the scale divergence term become. Okay, and once we see what that scale divergence term is, we will have our loss function, right? Once we see what the scale divergence term is, we will have our loss function, and then we can analyze that loss function, right? We can see, okay, what is, uh, I mean, what is that loss function telling us? What is it that we are actually doing? Things like that, okay? So that is where we are headed. So next class, we will look at the scale divergence term. That's all, and sort of finish the major chunk of diffusion models and like maybe like talk a little bit more about the intuitions or insights into the diffusion model. Yeah, right.
Yes, and uh, would you be conducting some one or two, sessions by using, since lot many libraries are available of diffusion models nowadays, to just to
Yeah.
give a demo that what are the potential use cases of the diffusion models available?
What I can do, I think, is perhaps because doing a demo tutorial is would be like quite honestly I don't have a lot of materials on that, like which tutorial I should see and things like that, because I have also learned the practical sides of all these things by hit and try. Like I have learned it from scratch by looking at different tutorials. What I can do perhaps is share those materials.
Yes, that would
uh
also be. Yeah.
yeah, right.
Can you name the library which you used?
Okay, I mean these diffusion models are mostly implemented using the diffusers library. That is what I'll use. There's a diffuser library that you can use to implement like do experiments on stable diffusion and things like that. There are also other repositories. Maybe I'll share those repositories. Like that's not an issue. Yeah.
Sure, sure. Yeah, that would be helpful. Yeah, thanks.
Right. Let me stop the recording. Yeah.